If you haven't done so yet, please pause the video and try to answer the question on your own before listening on. The question tells us that charges Q1 and Q4 are both equal to capital Q, so we can go ahead and label those two charges. And then charges Q2 and Q3 are both equal to lowercase q, so we can also label those. Now, we don't know the magnitude nor the algebraic sign of these charges, but for our purposes, we're going to assume that capital Q is a positive value and that lowercase q is a negative value. And these are assumptions, but it turns out that this problem would work regardless of which signs we choose for capital Q and lowercase q. These just happen to work out nicely for our purposes, so we'll just make that assumption for now. Now, what we will do is focus our attention on the charge that's labeled Q1. And what we're going to do specifically is draw the forces that are acting on that charge. Now, since we're assuming that capital Q is greater than 0, we can put a little positive sign next to it, as well as for charge 4. And then the lowercase q's are negatives. So we'll put those signs next to them as well. Now, charge 2, because it's negative, would be attracting charge 1. So it's going to be pulling on it to the right. And we can perhaps label that force as F21. That would be the force that charge 2 is exerting on charge 1. Charge 4, because it's positive, would be repelling charge 1. In other words, it would be pushing it away. So we can show a second force acting on charge 1 that is sort of directed in this fashion. And we can label that F41. That would be the force that charge 1 is exerting, that would be the force that charge 4 is exerting on charge 1. Now, charge 3, being negative, would be attracting charge 1, so it would be pulling downward on that charge. And we can label that F31. That would be the force that charge 3 is exerting on charge 1. So there are the three electrostatic forces acting on charge 1. What we want to do is look at the sum of those forces in the x direction first. And if we look carefully, we can see that F21 is acting exclusively in the x direction and that it's positive. So we would have positive F21. F41 would have to be broken up into components because it's acting at an angle. Now the drawing is going to get a little tight here, but we would have an x component pointing to the left as well as a y component pointing up. Now, because this is a square, we know that the diagonal of the square would be forming a 45-degree angle. And therefore, this angle here will also be 45 degrees. And that means that the x component of F41 is going to be F41 times the cosine of 45 degrees, because this x component is adjacent to the 45-degree angle, so we'll be using cosine. And furthermore, it's pointing to the left in the x direction, so it will be negative. So we, in summary, have minus F41 times the cosine of 45 degrees. And then F31 is acting exclusively in the y direction. Hopefully we can see that there is no x component to F31, so we can exclude it for the sum of the forces in the x direction. We can set these forces equal to 0. Now, how do we know that? Because the question says that the net electrostatic force on particle 1 is 0. And that means that the sum of the forces in the x direction has to be 0. Now, we're going to expand the expression for F21 as well as the expression for F41. For F21, we would have the Coulomb's constant multiplied by the magnitude of the two charges and then divided by the distance between them squared. Note that the distance between charge 1 and charge 2 has been labeled as A. Let's also not forget that charge Q2 is actually symbolized by a lowercase q, and that charge Q1 is symbolized by an uppercase q. For F41, we're going to have a similar setup. Now, notice for the distance between charge 1 and charge 4, we would be needing the length of this segment right here. Now, in effect, since we have a square, we have ourselves a 45, 45, 90 right triangle. This side has been marked A, as has this side. That means the hypotenuse here is A radical 2. So we can plug that in for the distance and then square it. Q1 and Q4 are both capital Q, so we can replace those. And in order to solve for the ratio of capital Q to little q, we're going to add this entire blue term over to the right-hand side. We could then square out the denominator here to make 2a squared. We can cancel the a squared on both sides of the equation, as well as the k's, and also a factor of uppercase Q. We can also remove the absolute value from the uppercase Q because we have stated it to be a positive value. And also the cosine of 45, of course, is radical 2 over 2. So on the right-hand side, we actually have capital Q times root 2 over 4. And then we're going to multiply both sides of the equation by 4 over root 2 so that these cancel. And then we'll divide this absolute value of Q over to the other side. Now, if we punch this into our calculators, we get approximately 2.83. But we've got to be careful because remember, uppercase Q was a positive value. Lowercase q is actually a negative value. So when we have a positive value divided by a negative value, our ratio, of course, is negative. So we have to make sure we stick a negative sign on here. And then this would be the correct answer to part A. Now, for part B, it turns out that the answer is going to be no, but of course we want to explain that. So what we'll do is actually take a look at the net force that's acting on charge 2. Now, of course, charge 2 would be attracted towards charge 1 because they're opposite signs. We can call that force F21. We have an attraction pulling charge 2 downward. We can call that F24. And then charge 3 is actually repelling charge 2 in this direction, and we can call that F23. Let's look at the sum of the forces in the y direction and set that equal to 0. We can see that F21 is acting in the x direction, so we can ignore it. But we do have a downward F24, so we'll call it negative F24. And then we have F23. That needs to be broken up into an x and a y component. And so we'll have F23 times the sine of 45 degrees. That would be the y component of F23, and we'll set that equal to 0. As before, we'll replace the expressions F24 and F23 with the correct setups. We'll add the blue term over to the right-hand side. We'll cancel a factor of q, as well as the a squared, as well as k. And then when we algebraically rearrange this, we're going to have radical 2 over 4 is equal to capital Q over Q. Remember, that'll be a negative ratio because capital Q is positive, lowercase q is negative. Well, radical 2 over 4 is approximately 0.35. This is a different ratio than we had obtained in part A. So because we obtain a different ratio, our assumption that the net force in the y direction acting on particle 2 equals 0, that assumption was unfounded. And because that assumption was unfounded, it's not going to be true that we can have the net force on all of the particles equal 0. So once again, the correct answer to part B is no, because we obtained an inconsistent ratio, something different than that we obtained in part A. Thanks for watching. If you liked the video, click the thumbs up icon and subscribe. You can send in your own question to this email address, and I'll do my best to answer it on